Hi, I'm Danae Brazel, Vice President and General Manager of KIN-TEK Analytical Incorporated. Thanks for your interest in the topic of creating controlled percent relative humidity for calibrating gas monitors, sensors, and detectors. First, let's discuss what relative humidity is and how it is defined so that we can better understand why it may be important to include in a gas calibration system. So in general terms, when we speak of relative humidity, it's the measure of water vapor and air expressed as a percentage of the amount needed for saturation at that same temperature. In other words, air can only hold a certain amount of moisture at a given temperature. So if it's 86 degrees Fahrenheit outside, it can only hold about 30 grams of water vapor per cubic centimeter. So why is percent RH important for calibration? Well, there are a lot of reasons why a lab, manufacturing, testing, or process facility may need to calibrate for different levels of relative humidity. Calibration should be done in the same conditions and the same true operating conditions in which equipment is used. Humidity can interfere with gas analysis, can cause false readings, so any calibration should be done with the percent relative humidity that's in the atmosphere. Humidity also causes corrosion and degradation of parts, and humidity can react with the gas mixture. So for those reasons, if you're working with detectors or monitoring devices and you need to calibrate those devices and they're being used in humid environments, you want to mimic the same true operating conditions when you do your calibration. Devices that require calibration and that should account for the amount of humidity in the gas standard are atmospheric detection devices such as thermal desorption tubes, gas detectors in process areas, clean room monitors, gas sensors, and direct humidity measurement devices. All of these are used in the atmosphere in which they should be calibrated, so you want to add relative humidity to that calibration to make sure you're getting the true readings. So all that's fine, but what really is needed for creating gas standards with percent relative humidity? First, obviously you want the gas standard. So you want a dry gas standard that you're going to humidify. You need that gas standard to be accurate. So accurate gas concentrations. In addition, dilution gas is needed for doing a calibration curve, whether you're using various cylinders of a certain gas and you want to dilute it, or you're using various cylinders of gas concentrations, different gas concentrations. But either way, your dilution gas is most likely going to be needed when you're doing or creating a gas standard for calibration. Flow control devices, temperature control or readout devices. You also are going to have to calculate the percent RH values based on measured values. So whether you're measuring the temperature of the room or the temperature where you're testing and or pressure or anything that's going on in the atmosphere of what you're calibrating, you're going to have to measure those devices and then calculate them on the fly. You would also need devices to create various percent relative humidity. So that's the key there. So you're creating a calibration gas up here. So you're actually creating your dry gas, your calibration gas, whether it be a VTEX mixture or whatever, but you're also wanting to humidify that in a percentage that is indicative of the environment in which you're working. So you have to create that percent relative humidity without interfering with the gas concentration. So those items are important and are needed for doing your calibration properly. But what are the methods available for adding a known percent relative humidity to a to a gas calibration? Well, you have saturated salt solutions in a closed chamber. That is a possibility. It's a little bit difficult to work with. 2 temperature and 2 pressure chambers are also a possibility for creating percent relative humidity for your calibration gas, as well as bubblers, headspace saturation, and a split flow saturation chamber. For our purpose of controlling percent relative humidity, we found a split flow method to be the best operational method for working with. But we have to consider that the challenges are not just equipment and the controls, but it's also the delivering of the gas mixture. So you're creating that calibration gas and you're humidifying it, and that's great that you're creating it, but how are you going to actually deliver it to your detection device or your your monitor for calibration? And considering the aspects of creating the percent RH and also delivering it, we have to look at all the challenges. So what are the challenges? Well, first we got the creation of the percent RH in a gas mixture. So we got to put that together and make sure that we're not losing the gas to the percent RH. We also have to deliver to our device under test, whether it be a sensor, detector, monitor, or analyzer. And we have to maintain the gas standard concentration despite any changes we do to the percent RH. So there's a lot going on there. We also have to maintain dry and wet flow ratios for creating first the gas concentration and then the controlled percent RH. This involves pressure control, temperature control, and then obviously calculating those changes during those adjustment cycles. So when we change the different percent RH, we have to calculate and reassess what that adjustment has done. KIN-TEK has a great solution to address all the challenges that I just discussed. It's the FlexStream permeation system. It uses permeation tubes in the base module that dynamically create the gas for calibration. So we create a dry gas there with the calibration gas mixture, whether it be BTEX, H2S, so on and so forth. And we can do the flow changes within the permeation system to create a gas calibration curve. Adding the relative humidity module, which is the HG module or FlexStream HG module, we then can do a wet and dry gas ratio in a split flow saturation chamber to allow for total flow for the percent RH that we need and also for the gas concentration values that we're looking for. Percent RH can be set and sustained to a plus or minus 3% window. This typically can be tighter if needed. It just depends on the controlling aspect of your delivery. Calibration gas mixture can be humidified without interference or reaction using the split flow method. Both flows, both the wet and dry gas flow ratios, whether it be the dry gas with the, say, H2S added in, or the wet gas, both of those are in vapor form, so there's no interaction or reaction or interference from the percent relative humidity. And then so we're maintaining concentration, and the percent RH changes are calculated and adjusted automatically. Results are logged and can be exported. So here's an example of the FlexStream permeation system with the humidified gas module or the HG module. So you have the FlexStream as a base module here connected to the HG module here. So we have two modules connected together. The FlexStream base module has a touch screen that allows for scrolling through the different modules that are connected and looking at the controlling screen for that for each of those modules. So everything's controlled through the base module and that touch screen. It also has software that allows you to do controls too, and we'll look at that here in a second. In this scenario, we have the base module with the dry calibration gas mixture coming out of it and going into the humidification module here. That gas is then combined with the wet gas or the saturated gas that's being created by the humidification module, and it exits out of the system, which then comes around and crosses a sensor sitting in the sensor block. So in this scenario, we're actually looking at a set point of 20% RH. We're getting 17.8, and if you remember, I have that plus or minus 3% default that I'm working with, so we are within our plus or minus 3% here. We get the 20% RH. Our flow level is about 1,315 cc's of flow. 325 of that is wetted or basically saturated flow, and then the other part is dry flow coming from the base module. That's the flow that contains the base module that's creating the, say in this example, 5 ppm H2S gas from a permeation tube that's giving 10,000 nanograms per minute emission rate. So as the gas exits the whole system, as pointed out in the previous slide, we have the flow coming across an external sensor. This external sensor is connected to the FlexStream system, and when using humidified gas or an HG module, the system uses this external sensor and it relies on that for the percent RH and temperature reading. It then controls based on this sensor as a feedback mechanism to readjust or align the output flow to stay on the concentration value that we specify. So if we do, as I say, in the case of the 5 ppm H2S, we need a flow that will give us the 5 ppm H2S, a total flow, and we want to humidify that. So we have to control everything upstream based on the sensor reading here on this external sensor. This external sensor is seated in a sensor block, and it allows for free-flowing gas across it. So we have to have no back pressure buildup that would affect our reading here. And we are monitoring the percent RH and temperature with this external sensor. So if we look at some of the data that has been generated from using the FlexStream permeation system, we can see that our primary dilution flow rate it was around 985 cc's per minute. Okay, as I mentioned before, we wanted to get about 5 ppm of H2S coming from our system. So we have to maintain that concentration. This is a run of about 20 minutes, just averaged data for that 20-minute run to show how the system controls. So primary dilution flow, that's our dry flow. So we had about 985 here. We had an average of about 325 here for the HG flow, meaning that's the saturated flow. So putting those two flows together gives us our percent RH. Now we have, and we can see over our 20-minute span, we had 18% RH, which is well within our plus or minus 3% window. And then we did maintain our 5 ppm H2S. So we can see here, we created our calibration gas. We held it within the plus or minus 3% RH that we desired or that we set. And we did that by varying the flow ratios here. We can see the FlexLink software and the readout on the FlexStream software, and we see the stepwise change between 20% to 50% to 80%, and then finally 90% relative humidity. So this FlexStream, this is a FlexLink software that comes with the FlexStream system, and we can see the graphical stepwise changes over time. These runs are anywhere between 20, 30 to 40 minutes. So 30 to 40 minute data runs. We ended up here with 90% relative humidity. Just to point out, our device under test temperature where our sensor was located, our external sensor, we're showing about 22.1 degrees C that day that we ran this test. And internally in the HG module, we can see that we were creating 69.9 or 70% relative humidity at a temperature of 28.4. So as it exits the system and then goes out to the external sensor, that temperature is different there, and then we're actually creating the device under test relative humidity. So that's, again, the value shown at that external sensor. So we can create a stable percent relative humidity in our gas flow, which in this case I'm looking at the humidified gas module, that flow being 962 at this case for the 90%. So we have a higher saturated gas flow for our 90% setting, and obviously a lower dry gas flow to get our concentration. So we maintain our total flow to get our concentration, as well as provide the relative humidity that we need in these stepwise changes. The red lines here, if you can see on here, we have a couple of red lines. That's our plus or minus 3% window. You can see that here, plus or minus 3% error shown by the red line. The green line is our set point, and then we have the white line as it tracks close to the set point within that plus or minus 3% window. So the software itself shows you this monitoring aspect as you're creating that calibration gas. Well, I showed most of my data from using the sensor block that I showed you, where the RH sensor was set in the sensor block. I wanted to actually address how it would work when using a chamber. So I put together a small chamber. This is about a 1 liter capacity. The sensor is situated down in the chamber, but it's in the flow path, so you can see how my external flow coming into this chamber would cross that sensor so that I can actually monitor what's going on in that chamber. I do have small flows in this chamber so that I'm not building up pressure. I don't have a pressure buildup, so I need to maintain my fresh environment and not have that pressure buildup that would change my concentration and or change my relative humidity. Theoretically, I could open this up, put some sensors in here if I was developing sensors, and make some slight modifications to put those sensors in there, and then I could test in that environment those sensors and how they're being exposed to both the gas mixture, whatever calibration gas I'm using, H2S, BTEX, any other harsh chemicals that we would want to look at, and expose my sensor here, as well as create the relative humidity that I need. So if I incorporate a chamber, I need to look at how that would change versus just using the sensor block and crossing right before I would go into a test chamber. So general results of the test with the chamber show some delays in stability before achieving our plus or minus 3% window. All I did was take a cutout of that graph from the software and as a comparison here. So here we are at 30%. We did maintain our 30% relative humidity, but as we go to that stepwise change up to 50%, we see some longer time basis here for it to stabilize back to the next setting. And from going from the 50%, you can see then we did stabilize, but going from that 50% up to another stepwise change to 80%, we again have a little more oscillation in that stabilization. The 80% within the chamber, probably because of just that stepwise change, had a little more transitional stability that it had to go through. We had some oscillation. We did stay within our plus or minus 3% window for the most part, and you can see that when it does bounce out of that plus or minus 3% window, it works to control within it. So it does make the adjustments to stay within that window. We then took some time here for that stabilization. We see that oscillation, and then it does stabilize. So that's some good data there showing that, yes, while we have a little bit more of a stabilization change from the stepwise changes, there's a little bit of time for stabilization that has to occur. We can go to a small chamber and get good results in the long term if we just give it time to stabilize. Okay, I've shown that we can create a gas mixture from the flex stream permeation system and apply a variable percent RH at different step changes. And we can do that for stabilizing a concentration and delivering that concentration and the percent relative humidity to a device under test. But some of the possible improvements that we need to consider are controlling the gas temperature or the chamber temperature. So whether it's going across a sensor block or going into a chamber, that gas temperature does play a role when it hits that external sensor in the feedback controls that it does with the flex stream system. So the other thing would be to determine the optimal chamber size for best stability. So I had about a 1 liter chamber that I was working with. A larger chamber, it may take longer for it to stabilize. We saw some instability with the small chamber, but having that optimal chamber size and allowing that free flow may be a good improvement. Measure or validate readings with other sensor detectors. So you can put another sensor or detector within the chamber or the sensor block, but you still got to calibrate that. And so you want to make sure that that's calibrated a certain way as well. And then test the responses based on tighter accuracy. My window was plus or minus 3%, so going to a 1% and seeing how the stabilization works would be a next step. Allow broader pressure control and flow control ranges. Sometimes on the borderline flow control and pressure control, the system will bounce out when it's trying to stay within that plus or minus 3% window. So maybe allowing some broader controls there would be a good improvement. So in summary, we showed that a calibration gas with percent RH ranging between 20% to 90% can be created. We showed that it also can be delivered to a detector, sensor, or monitor using the flex stream system with the bulkhead sensor. And then we took it a step further and showed that we can do this across a chamber or inside a chamber as well. However, the chamber needs to be constructed in a way that provides optimal stability. We know that control of pressure, dry-wet gas flow ratios, and temperature is important, and that controlling the percent RH is going to require automatic monitoring or adjustment for stable long-term results. So the FlexStream automated permeation system with the HG module provides those controls needed for both creating the calibration gas and delivering the calibration gas with controlled percent RH in the calibration gas mixture. So thank you for your time today. We appreciate your attention.